the organizers and also for you as the audience. Okay, let's see if we can get this shared. Excellent. Okay, fantastic. So as Daniel said, I'll be talking about a form of distributed zero knowledge and applications. In fact, particularly focusing on this set of applications in regard to secure computation. So what I'll be speaking about, it's a collection of joint works. The union of such authors are Dan Bonnet, Henry Corrigan Gibbs, Niv Gilboa, Yuval Ishai, and Ariel Nof. So it's interesting to me. I saw that this workshop really actually hasn't touched much on secure computation, which in some sense I think was one of the original really killer apps in this direction. So I'm going to be making a change on that. And in fact, let me start out kind of in the opposite direction with what is secure computation and why is this motivating us to look at a particular type of zero knowledge? Okay, so probably most of you guys have seen this, but just to be sure. So secure multi-party computational, sometimes called this MPC. These are protocols where the goal is to take collection of different non-trusting parties that have some form of secret data and to compute jointly across this data, but without revealing the data itself. So we'll sort of formalize this. Suppose that we have some function f. This is a public function. We know that we want to compute this. And an MPC protocol allows us to somehow magically learn f applied to the collection of all of our inputs, but without revealing anything else about the inputs themselves. This should take place even if some subset of the parties who are playing a role here are adversarial. So for example, they're colluding with each other, they're sending bad messages, and so forth. Okay, so certainly this has a real flair of zero knowledge. You learn nothing else beyond something. And in fact, as I said, this is one of the original main, or one of the big applications of zero knowledge. So this is dating back after the original zero knowledge paper in GMR in '85. Shortly thereafter, there were a couple works of these likely characters, so GMW. This is Goldreich, Mekali, and Vigdalson. And they showed that zero knowledge can be a really important tool in protocols for MPC, and actually even beyond that, in this step of the following. Okay, so ultimately, we want to design protocols that are secure even against malicious adversarial behavior. Okay, kind of capturing whatever these guys could be doing. This actually rather cute, but very, very bad adversary up here. And starting with these works, and in fact, basically everything after that reaches this top step by first designing something that's a weaker notion of security, which we refer to as passive versus active security. Okay, so whereas active, people are actively trying to ruin your life, passive security is a weaker notion where you assume that actually people do follow the protocol honestly, but that they're just combining information in ways that they're not supposed to try to infer additional things. Okay, and what these works showed is that you can generically go from a passively secure protocol, which is much easier to build, it's a much more reasonable target, and compile that protocol to one that's secure against the stronger active adversary. Okay, this step is this jump up from passive to active is really one of the underlying focuses of my talk today. And let me just say very briefly that this is a topic of a lot of research. So since the original GMW transformation, there's a lot of different ways of doing this, different approaches. That in fact, a lot of them look quite different. And it still is an important area, that there's still work to be done trying to minimize this induced overhead in this step. So in this first part, I want to kind of start zeroing in on motivating what is this distributed zero knowledge. And to do so, let me zoom in a little bit more on what the original GMW compiler was, going from passive to active. Okay, so we suppose that we have some protocol that's secure against passive adversaries. Their idea is to somehow kind of prove, okay, that in fact, in their compiler, it was actually for every single message that somebody was sending in this compiled protocol, together with the message in the underlying protocol, they would also prove that this is indeed the message I'm supposed to be sending, okay? And this was via zero knowledge proof, where the statement, okay, is the collective protocol transcript, everything that's been seen up until now. And they needed to kind of combine this and prove that given all of the stuff that you see, this next message that I'm giving you is what you should be expecting. And this is, of course, done in Zeroknowledge. Okay, so this was a fantastic, really kind of monumental way of viewing things, and it's opened up so many different directions. But indeed, there are some limitations, and of course, a lot of these have been addressed, but I'm focusing just now here. That in this, this original framework, this statement, in order for me to prove to you this statement, you have to know the statement, okay? Which means that I sort of need to, for example, the fact that I'm sending the right next message depends on all sorts of stuff that I'm sending you, and so forth. So to achieve this with the GMW method, it needed to be the case that this was all kind of everybody knew all the joint information that was necessary in order to make this proof. Okay, this ends up leading to a lot of overhead. So for example, I have to kind of encrypt everything, commit everything. This necessitates cryptography. There's more overhead in communicating things maybe I didn't necessarily need to communicate. And the statements that you end up proving are more complex. And let me make a brief aside here that, of course, you can minimize some of the communication and so forth by using a lot of machinery like sublinear Zeroknowledge, snarks, and so forth. But the trade-off there is very heavy in terms of the computation that you have. Okay, so just kind of to keep in mind, a lot of these cheap protocols, the operations that you're doing, or maybe something like symmetric operations per gate that you're securely computing, if I needed to do something like a snark in each step, exponentiations, this is on the order of maybe a million times slower. Okay, so because of this, I want to kind of shift the angle a little bit and consider a motivation of a lighter approach. Okay, so in particular, suppose, for example, that I am taking this framework that I want to prove to you that the messages that I sent in the protocol are correct, what I was supposed to send. Okay. But now, maybe it's some sort of protocol in different settings. And in fact, in some settings, if you want, say, to not use computational assumptions, it has to be that you're using secure channels, you're sending different people different pieces of information. And what that boils down to is that this statement, this collection of all of the message that I've sent and I've received in the protocol, this statement I know as the prover, I know it in whole. And the statement itself is held in pieces across the other players, the other parties, okay? So for example, this corresponds to the information that I sent or received from party P1. This is from, of course, P2 here, and so forth. Okay, now, so taking a look at this, first of all, there's a real qualitative difference that the statements that we're talking about are not something that have to be globally known by everything, but they're split across, okay? And it's gonna turn out to be that using this viewpoint, that the types of relations that we need to prove are gonna end up being much simpler. Okay, so for example, it'll be something like this message that I sent was equal to the product of this message and this message that I received. Okay, and we'll go into more detail on that later on. So all of this is very up in the air right now, but what I want you to get the takeaway from this is that it could be quite useful to be able to have a system where you can prove a statement where the statement itself is held across the different verifiers, okay? So now let's get down to some definitions a little bit here. I'll go deeper even later on. But just to kind of compare and contrast, so standard Zeroknowledge, you have the prover, you have the verifier, you're communicating back and forth, but both of them hold the statement. And the Zeroknowledge property is that the verifier doesn't learn anything beyond what he already knew, which was the statement, and that the statement is in the language you're proving. Okay, the analog here, a form of distributed, probably should be called distributed verifier. I compressed it for purposes of this talk. So distributed Zeroknowledge, here we're talking about Zeroknowledge proofs on data. And I want to emphasize here, it can be distributed in the sense that you have a piece of the statement, you have a piece, or it could be secret shared. So you have sort of additive, for example, secret shares of the statement. Really, the property that we need and what we're in the definition and what we construct is that there's some sort of linear combination of what the verifiers are holding on to that give you the statement itself. And you'll see why that's exactly what we need. Okay, so that's the starting point. Of course, you want some kind of soundness, but I want to emphasize that the zero knowledge property here is a little bit of a twist as well. Okay, for example, so say I'm looking at verifier V1. He, of course, he will learn that X is in the language, but we want to say that he learns nothing beyond beyond that and what he already knew. And in this case, what he already knew was not the full statement, but just the piece of the statement X1. Okay, and this will extend. So this is already a stronger property as well. Not only do we need, some kind of soundness when the verifiers don't have the proof in their hands, but we also want to make sure that by participating in the proof, they're not learning any more than whatever pieces of information they had to begin with. Okay, so this is the high level of where we're going to be going with this. And I have a couple kind of comments and remarks, and then we'll get more deep into the talk itself. So first of all, because of this different setting, that actually also sort of shifts the types of things that you could want or that you could hope for even. Okay, so the first main point is that because none of the verifiers, no single verifier knows the statement, that these things, these distributed zero knowledge proofs, or even forget about zero knowledge, even just a distributed interactive proof here, is non-trivial, and it's interesting already, even for very simple languages. Okay, so I'm going to be talking a lot about languages like there's a degree to relation of the values of the pieces of the input that's satisfied. This is not really something that we're trying to gain in terms of computational savings or so forth, but this is something that if I don't have the input, I can't even just verify on my own. Okay, and so some of the application settings where we're going to be using these things are a bit different than a lot of the standard use cases for perhaps for zero knowledge. So for just as one example, there's a lot of work now converting things. If you want to convert zero knowledge proof to a snark through an succinct non-interactive. For example, here in some of these transformations, you care about different efficiency metrics more than others. Okay, for example, there in some of the transformations, you care about things like the size or the complexity of the verifier queries, but you don't care, for example, about the proof size. This is something that you're kind of just computing in your head. Whereas here, in the applications where we're going to be using these things, I am actually going to be communicating the proof to people, or at least pieces of the proof. And for that reason, we will care about the proof size. So this kind of opens some really interesting new, even just directions of questions to try to answer. Okay, and one last remark before we continue is that this distributed verifier or distributed zero knowledge, there's a couple of different relations. I'm sure there's even further beyond this, but two that I wanted to point out that sound very similar, but actually are quite unrelated. So the first is, in fact, this is why I stuck the little hyphen verifier on my slide. Something that is called distributed zero knowledge. There's a couple different works there. This is a work of Wu et al., one of Ephraim et al. There, in that sense, when they're talking about distributed zero knowledge, their goal is to distribute the prover, and this is just for computational efficiency purposes. Another notion, so this interactive distributed proofs, it's a little bit more in the same direction. First of all, it is the case that the verifier is actually being split across different entities, but the goals and the questions are also quite different. So they're looking explicitly at the verifier consisting of different nodes of a communication graph, and they're trying to prove properties about the graph. So kind of in terms of our applications and so forth, it's going to be somewhat orthogonal. Okay, good. So we'll see what we get through today. I'm very optimistic. But what I want to do first, just a couple more words on the definition, diving a little bit deeper into two parts of it. I'll go through and talk about the construction approach and mostly focusing on what this core tool is that we use in order to build these things. So I'll say what is and a little bit about how we can get a fully linear PCP, IOP. For now, just leave that as a mystery of symbols. Okay, and finally, I'll talk about applications of secure computation. So a couple different ways that we can use these things. And if you forget everything else of this work, the two kind of underlying punchlines here, in addition to what is this new notion of distributed verifier zero knowledge, first of all, that we can get low cost, in fact, very short proofs for distributed zero knowledge protocols here for simple languages. And that using that, that allows us to get new compilers from going in this MPC setting of going from passive security to active security with very small overhead. So this is one of the first times that you can actually get sublinear communication overhead in this process. Okay. Okay, so let's be a little bit more explicit here with the definition. So the setting, as we've discussed, is that there's a prover and possibly a collection of verifiers, okay? Such that the verifiers each have some, think of it as some piece of the statement with the property that there exists some known linear combination of what the verifiers are holding on to that give you the statement itself. Okay, so as a couple specific examples to kind of keep in mind, this can be either that, for example, I own the first symbol of the statement, you own the second symbol, and so forth. Or, for example, that we have additive secret shares of the statement. Okay, the three properties that we want are the standard, our good friends here. So completeness, in the sense that if a prover is honest and X really is in the language, then this should be accepted. A little bit more refined now about zero knowledge. So here, I've described a case. You can consider many possible different verifiers. And zero knowledge should hold against any potential corrupt subset of the verifiers. Okay, so if you have a collection of colluding verifiers, here denoted by the set S, then it should be that after interacting with the protocol, you learn nothing beyond what you knew before. So that's the collection of these XIs that they knew, as well as the fact that whatever statement we're collectively holding on to is in fact in the language. Okay, and soundness here, I want to first consider an intermediate setting for soundness. Okay, so suppose first of all that we know that either the prover or verifiers could be corrupt. Okay, so verifier is corrupt, we already sort of dealt with zero knowledge. But suppose that now if a prover is corrupt, then the verifiers are all honest. Then the soundness that we want is relatively straightforward. That if the honest verifiers accept, that means that the statement that we're jointly holding is in the language. Okay, things become a little bit more subtle. I'm not even going to give a full formal definition here, but just point out a little bit that in the case where a corrupt prover could potentially be colluding with corrupt verifiers, there you have to take a little bit more care in the definition. So for example, even kind of defining what is the statement that we're jointly holding on to is not necessarily well defined. So in particular, to actually hope to get this notion, you have to assume some sort of robustness of how the statement is being held across the verifiers. Okay, so this is the notion. So the next I want to talk about the ways that we have of constructing this, okay? And as part of this, we'll take a little stroll through this side notion, which actually on its own, wow, okay, good. English is good. On its own is quite interesting, and it has a lot of probably questions yet to answer there. Okay, so this is going to be a notion that we'll call fully linear probabilistically checkable proof. Okay, and so in order to actually define this, let me sort of take you through a mini history of what other things do currently exist. Okay, the first of all, so this PCP, whenever I say PCP, although probably to this crowd, I don't need to describe this, I'm referring to a probabilistically checkable proof. Okay, so here what I've described in the picture is like the viewpoint of the verifier, that there's some statement, the verifier knows the statement, and is able to make query access, Oracle query access to the proof, and as a function of that decides if it's in the language or not. Okay, somewhat more recently, it was shown that a different notion here of linear PCP actually opens up a lot of different application settings. And so here, what's the difference between a PCP and a linear PCP? Again, it's the case that the verifier has the statement. Okay, but the types of queries that you allow the verifier to make are quite different. So whereas PCP is kind of point looking up indexed values, with a linear PCP, the verifier is allowed to take any linear combination. So they sort of put forth, I would like this vector of coefficients to be inner producted with the proof, and I just get the element that's the output of that. Okay, this is, as an abstraction, this ends up yielding a lot of really interesting compilers. Okay, but so both of these cases are obviously a bit different from what we've been looking at because they assume that the verifier sees the statement. Okay, so something that's more in the direction that we're going, which existed already back in 2014. Perhaps you've heard of the notion of PCP of proximity. So here, for in sort of similar to our case, the verifier does not have direct access to the statement, but instead can make queries to the statement. In this case, also like the standard PCP, where they can just query individual symbols of the statement as well as the proof. Okay, but one of the downsides of PCPs of proximity is that kind of inherently you can't really hope to prove via the outcome of one of these things that the statement X itself, the full statement, is in the language. Because, for example, if you just damage one piece of it, that's unlikely that the verifier is going to be able to see that this one piece of it was incorrect. So because of that, PCPPs or PCPs of proximity can only tell you that whatever the statement that's written here that you don't actually see, whatever's written has to be close to the language, that there can't be too many symbols that differ from something that is in the language. Okay, so now enter our fully linear PCP here. And this is kind of really taking the combination of the linear and the PCP of proximity approaches. Okay, so here the verifier does not see the statement and instead can make linear queries, but here the linear queries can span across the statement and the proof. Okay, so for example, I can consider some sort of actually, I'm not sure, did somebody just annotate that? Some sort of linear combination of proof statement, proof symbols together with statement symbols. Okay, and so analogous to all of these different notions also have a zero knowledge version. So I'm just kind of mentioning it for the bottom right corner here. But in particular, so for a zero knowledge fully linear PCP, this is kind of as you'd expect. So the verifier shouldn't learn anything beyond what he knew beforehand. In this case, he didn't know anything. He didn't know the statement, didn't know the proof. Okay, so he should only learn that X is in the language. Okay, continuing similarly. So back in 2016, there were these two different works jointly came up with the notion of sort of an interactive version of PCPs. So IOP here stands for interactive Oracle proof. And this is, so as they defined it, it's a notion where you can kind of give many different PCPs to a verifier in an interactive manner. Okay, so I give you sort of set a proof, the verifier can make queries as a function that send me some challenge, I send another proof, they make queries, a challenge, and so forth. Okay, and similarly, you can extend this in sort of the natural way to a fully linear version. So here the verifier, of course, does not see. Okay, so my strange day with technology. Good, here the verifier does not see the statement, but gets to make these continual sort of setting the proof, taking the linear queries, sending another challenge, getting another proof he can make linear queries for, and so forth. Okay, let's see. So here, of course, the zero-knowledge version is analogous to before. And just one kind of aside here. So in both of these cases of interactive oracle proofs, and also for the fully linear IOPs that we're going to have, it turns out that you can, without loss of generality, kind of push all of the queries themselves to the very end. So in this case, all these arrows or all these sort of linear guys. And what that means is that, and on top of that, that these messages can be basically random challenges. So what that means is that you can actually use the Fiat-Shamir transform for those who are familiar with this, which means that you can take this interactive thing and actually squash it down if you assume a random oracle. So you just have one round of communication. Okay, so this was, your your mini complexity lesson, I suppose. But the point here, so these two new tools, the fully linear PCP and fully linear IOP, they're interesting to me for right now, because you can directly plug and use them in order to get a distributed verifier zero-knowledge proof. Okay, so for example, let me give you the case. Suppose that I give you a scheme for a zero-knowledge fully linear PCP, okay? So how can you transform that? How can you use that in the previous setting where you have now, for example, multiple verifiers versus this fully linear PCP? There was a single verifier, but you limited the types of queries that he could make. Okay, and now we're sort of going to be in a case where there's multiple verifiers, and the only types of queries that they're going to actually be able to jointly answer to themselves will be linear queries. Okay, so explicitly, suppose that I have a zero-knowledge fully linear PCP scheme. Okay, so the prover will begin by generating a proof, okay, for his statement X. This, and recall, in fact, that the proofs can be quite small now. That's why I purposely made this a little bit smaller. So he generates the proof pi. And I want to keep this so it remains zero-knowledge. And remember that the zero-knowledge property of the fully linear PCP doesn't even let you see the full proof. You only can make these linear queries. Okay, so for that reason, I can't really give either verifier the proof directly. But what I can do is I can additively secret share the proof and send shares of the proof to the two different verifiers. Okay, and that's denoted here by these boxes. Okay, so now think of the verifiers. They have these shares of the proof. And what they're trying to emulate, the two of them together are going to try to jointly emulate the single verifier in the fully linear PCP. Okay, and recall that verifier says, I want to make this linear query. Okay, and it's a linear query on the statement and the proof. So what these guys will do, they need to somehow jointly generate the answer to what that linear query should be. And they'll do it by applying the linear query to their piece of the two. Okay, and because of the linearity of all of this, by taking whatever contribution verifier 1 has for the answer to this linear query, added together with the contribution of verifier 2, that added together actually gives me the answer to the linear query if there had been an oracle that had access to the real X and the real pi. Okay. So this, and in fact, this can repeat. So now as a function of the answer of this, maybe they want to do another query, so they can do the same process again, and so forth. And in fact, it also extends, I've described it now for the case where the prover doesn't continue interacting, but it goes exactly in a natural sort of way that if you were using an IOP instead of a PCP to start with, then what that means is that after the verifiers look at some things, they send the prover a message and he generates a new proof, secret shares it, and we continue from there. Okay, so this is like the abstract connection here. Okay, and now how do you actually build these bottom tools? Well, I'm not really going to get into that. I will say that in fact, if you look at the literature, implicitly a lot of these fully linear PCPs actually already exist. For our setting, we needed a specific sort of direction where we're interested in these simple languages and we really want very small proofs. So we ended up building construction, although it of course is very reminiscent and takes a lot of ideas and flavors of other works. In particular, it builds a lot on the SumChat protocol, which Justin talked about the other day. Okay, so kind of putting these together, I've chosen 2 points to highlight here. So for example, suppose that you have some language. This is a subset of length and strings over some field. We have fully linear PCPs with sublinear proof size. Okay, so here square root n for any degree 2 language. That is, that can be describable as some degree 2 function being satisfied of the pieces of this Fn. Okay, and if you allow interaction, so with log n rounds of interaction, you can actually get the total proof size down to very small, just logarithmic. And this extends, in fact, to any constant degree predicates over F. Okay, and note that, so these constructions, I didn't put any sort of assuming this or that because there are no computational assumptions. So these are information theoretic. And on top of that, so they extend for fields, also for rings of the form Zn. Okay, so now we have come to the final part where I want to tell you, so now suppose that you have in hand some sort of distributed zero knowledge proof system, okay, for useful classes of predicates. Okay, let's go back now and try to figure out how to use this for multi-party computation. And the real focus when I'm going to be trying to design efficient protocols and talking about the step from passive to active. And my focus is going to be on what is the communication complexity of doing this process and of the eventual total protocol. And just a note here, so I'm focusing on communication for a couple of reasons, but one of which is that it actually tends to be one of the dominating factors of the complexity, the cost, the end-to-end runtime costs of these protocols. Okay, so I posed a question, what is the communication complexity? And there's a simple answer, I suppose. Of course, the technology behind it is not simple. So if you allow yourself to use, fully homomorphic encryption, related tools, then theoretically the communication complexity is very small. It scales just with the size of, say, the inputs and the outputs of the communication of the computation. Okay. However, I'm going to be kind of pushing those to the side, even though obviously I'm also interested in these directions as well. And what I'm going to be focusing on and everything I'm going to be describing after now is going to be in a case where I'm not allowing heavy machinery. And this I can actually formally define by saying the only cryptographic tool I allow you to use is black box access even to a pseudo-random generator. Okay, so for example, things like in particular fully homomorphic encryption, even things like snarks and so forth are not going to be options for us based on this setting. Okay, so once you look at this setting, and by the way, this is not an arbitrary choice. This is not my choice for sure. But this is kind of, if you look at the vast majority of implemented MPC protocols, they lie in this setting. Okay, so here in this case, if you're restricting yourself to this setting, then we don't know how to do just communication inputs plus outputs, but instead what it boils down to is some constant, and in fact a relatively small constant number of elements per party. So here elements, I'm talking about, say that you take the function that you want to compute, you represent it either as a Boolean or some arithmetic circuit, and now those are the elements that I'm referring to, either, for example, bits or ring elements or field elements. Okay, so this is where we stand, kind of a small constant, and there's a tremendous amount of work that's going toward trying to get this constant as small as possible. Okay, so to date it's something greater than or equal to 2, at least to date, before some of the things I'm going to be telling you about. Okay, and now, of course, I have not forgotten about this ever important step of going from passive to active. And this is actually really a central piece of the cost here. So for example, there's a lot of really kind of satisfyingly efficient protocols if you're just looking at this passive security level. For example, alpha can be all the way down to just one ring or field element per party per gate. Okay, and unfortunately, the step of going from passive to active is where a lot of the costs are coming into play. Okay, so ultimately, what my goal here is going to be, and we'll show you how to get there in a couple different ways, is for the overhead, the communication overhead of going from passive to active to be sublinear additive overhead. Okay, so in particular, if you have some passive secure protocol that requires alpha elements per party per gate, and I want it will be the case here if we can achieve this, that the active secure protocol will have the same amortized alpha elements per party per gate. Okay, here amortized because there's going to be some sort of additive overhead, but amortized over the size of the whole computation circuit. Okay, so good. Okay, yes, I'm actually hiding what some of these protocols look like. So let's take this at a very high level here, okay? And the plan is going to be to start with a passively secure protocol that has a nice type of structure. And in fact, if you look through the literature, almost every single protocol has these kinds of nice structure, okay? And the structure in particular includes the fact that there's a first part of the protocol, which is everything except for the very final step. Okay, we'll call this pi prime. And then you send the final message. Okay, and such that with the property here that this first part, if we stopped right here, actually nobody learns anything. And there's certain properties that if they're satisfied, then it's safe to translate the final message. Okay, so our approach, of course, is going to be to try to stick something in here. We'll first run the semi-honest or passively secure protocol, okay? And then have insert a procedure which will somehow use zero knowledge so that people can prove that everything was done correctly in the first part. Okay, and then if that all passes, then you're free to do the final message. And if not, if any of the parties reject, then you're going to abort. Okay, so this high level structure, this is not new, but what is going to be new is what we're going to stick in this blue box region of how will we take the approach of actually proving that it's safe to continue. Okay, and I'll actually show you a couple different ways of doing that. Okay, the first, which I'll refer to as the type 1 compiler, okay, is sort of actually taking more of an inspiration from the original GMW compiler. And the idea will be that each party will separately act as prover to the other parties to prove that all of its messages in the earlier part of the protocol, this gray part before, were correct. Okay, so each of us will kind of take turns. We'll do this. If everybody passes the test, that means that everybody individually acted honestly in the original part of the protocol, which means that it's safe to continue. Okay, so explicitly, let's take a look what's going on here. So the statement, say we're focusing in now on one particular party who's acting as prover. So his statement is indeed the collection of all the incoming and outgoing messages of the first part of the protocol. Okay, and he needs to assert, so if you look at a lot of these natural protocols, it's really actually a very simple property that needs to be satisfied to say that these were the correct messages. I even alluded to this at the very beginning. Okay, so if you take all the subsets of these messages, those that I sent and received between myself and the first party, those that I sent and received with the second party, it's the case if you look at a lot of these protocols that the property you need to prove is literally just that, for example, this message here that I sent you is equal to the product of this message that you sent me and this message that somebody else sent me. Okay, that is that there's kind of abstracting out that there is a simple degree 2 relation on this vector x, which you can view as a vector of, depending on what your circuit is, either field elements or bits, which I suppose is an example of field elements, or ring elements, okay? And what you're trying to prove is that this vector indeed satisfies this degree 2 relation. And this is perfect, okay? Because this is exactly the framework that we have solutions for. It's exactly where we have the distributed verifier who have pieces of the statement and this degree 2 relation, we have sublinear size proofs. Okay, so plugging this in, what do we get? First of all, one note is that the soundness, so the soundness error of a potential cheating prover scales as 1 over the field size. Okay, so if your field is already big, then you're good to go. You just plug in our protocols. If your protocol is over a small field, okay, for example, we had a Boolean circuit, then 1 over 2 is not very satisfying. I get you there, okay? But don't worry, because what you can do is you run the original protocol exactly as you would with a Boolean circuit, okay? And then the only thing you need to sort of blow up to expand out is the proof portion, okay? And what you'll do is you'll prove that this degree 2 statement holds in an extension field, okay? So not just in the F2, but in some F2 to the L or something, okay? So it's true that the costs of the proof part will expand, but since this is all anyway sublinear in the circuit size, this expansion of this sublinear additive term still stays sublinear. Okay, and this is actually, I want to emphasize, because if you go into the literature, there's so much work that goes into trying to, for example, have special solutions for Boolean circuits, exactly because of this issue, where you get that if you're trying to run simple tests like this, you get only 1 over field size correctness error. And kind of, you know, amazingly, I think this approach automatically allows you to get that with very low overhead. Okay, so this is type 1. It turns out this is fantastic for the 3-party case with 1 corruption. Okay, and the reason here is because there you're exactly guaranteed that either the prover or the verifier can be corrupt. Okay, and so this exactly plugs and play, gives you this very low overhead. It turns out that this type 1 approach doesn't directly work if you have more parties, or more specifically, if you have more corruptions, okay? And here is exactly, as I mentioned before, that you have challenges with the case where a prover could potentially be colluding with corrupt verifiers. Okay, so for this case, we have a different type of compiler, okay? And what ends up happening is that the parties jointly, okay, so just to kind of recap, the first version, you had each party was proving individually, was acting as prover to prove that his part was correct. In type 2, what will happen is that all of us, all of the parties will jointly emulate the actions of a single prover. Okay, and now of course the statement is not that, you know, my messages were correct or anything like that, but what you can directly do is go to the circuit itself. Okay, and in many of these other protocols, what happens is that from gate to gate, I thought I had a picture here, but apparently I don't. From gate to gate in the circuit that you're evaluating, you end up jointly evaluating basically secret shares, robust secret shares of whatever value is supposed to be held on that wire. Okay, so now the new statement is the collection of all the secret shares that we're holding on to for all the different wires of the gate, wires of the circuit. Okay, and the statement that you're proving, which is also going to be a low degree, a degree 2 statement, is just that whatever we're holding on from this wire times whatever we're holding on from this wire, these multiplied is equal to whatever we're holding on to for this wire. Okay, and it's sort of the collection of all of those jointly. And this, so here, this is again a degree 2 statement. We end up needing to kind of use extra properties that here the prover itself is a low degree process for this case.
Just 1 second, you have 5 minutes left.
Oh, perfect. Okay, great. Thanks. Okay, I'll speed up a bit then. So kind of putting these, the type 1 and type 2 together, let me just kind of say, where does this lie in the state of the art? So in the 3-party 1 corruption, you can use the simple type 1. And this ends up getting us, so the comparison before us, remember this alpha refers to how many elements per gate per party did you have to speak at the end of the day in the actively secure protocol. Okay, so beforehand, if you had a large field, this was already 2 times overhead over Boolean. I said you have to do all these special things. You get 7 times, and using our approach, you get 1. Okay, because it's this sublinear additive overhead just for this one piece. Okay, for n parties and t corruptions here, so any honest majority, but t can be, of course, bigger than 1. It's a little bit more complex. So over a large field, you could get 3. Over Boolean or rings like 2 to the k, alpha was some big number, larger than 40. So we don't quite get 1 here, but that's actually just because the best semi-honest also doesn't get 1. So we do have sublinear additive overhead, but putting these together, we get that the total alpha is just 1.5. And this includes Boolean, this includes any Zn, and this includes any other field. Okay, so the last thing I want to touch on, and I will keep it quite brief. So the results that I described before are for the case where you have an honest majority of the parties. I can ask a question, what if you don't? What if you have a dishonest majority? So most of the guys are bad. And let me just say, wait a second. This seems like a bit of a problem. In fact, this was already a real challenge, even when we had more than one corrupt guy, even when we did have mostly honest. And we have a real problem that in order to consider a case where a colluding prover and verifier might be dishonest, that we need some sort of robust sharing of the statement across the parties. And how can you even hope to do that if a majority of the people are dishonest? Okay, so just leave you with a teaser here. This is very new, BGIN ? Because it's in submission right now. And what we're able to do is extend this approach to this machinery of using distributed zero knowledge also in the dishonest majority case. Okay, so we end up getting a protocol that's in the pre-processing model. Here, there's sort of a pre-processing phase that's independent of the inputs and a cheap online phase. I'll just say, I guess, one word about all of this is that you can view, so very, very loosely, let me even push aside all the details here. Kind of the idea is that you're going to emulate an additional verifier, okay, who's guaranteed to be honest. So say you have all of the parties, most of them are probably dishonest, but one verifier is going to be emulated by all of us, and that guy I know is honest, okay? And this allows us in a different sort of way to get robustness of these statements and robustness of the results, okay? So the punchline of what we get in this recent work is that, so there's 2 different sort of metrics you really care about in this setting. One has to do with how much pre-processing do you need to take from the offline to the online, and also how much do you need to communicate on the online phase. Okay, and in all existing solutions, at least one of these had a linear overhead. And now using this, this new technique, you can get it so that both are simultaneously sublinear in the circuit size. Okay, so before I get kicked out here, let me go ahead and summarize. So hopefully you've learned a bit about this new notion of distributed verifier zero knowledge, including these constructions, going through fully linear PCPs and IOPs. The fact that we can actually achieve these with short sublinear size proofs for simple languages. You're sublinear in the statement size. You don't need any computational assumptions. You can do this over general fields and rings of the form Zn. And that this is a lot of different applications to secure computation in taking the step of compiling from passive to active security. Okay, I won't take too much. So let me just quickly say 2 open question directions at least. So one is building these things. And the main focus here, why is this new and interesting? Because there's a lot of maybe not expected simple specific languages that we have motivation for because of different applications like multi-party computation. And it could be really interesting to try to zero in on these and actually get more efficient constructions for them. Okay, and there's clearly, even on the MPC side, there's a lot of space to still explore. I've talked about compilers for certain types of protocols. There are other types of protocols that don't quite fit into those structures. It'd be really interesting to see if we can find transformations for those as well. Okay, and with this, I will conclude, and I'll be happy to take, if we have time, any questions.
First of all, thank you so much, Elette. I'll applaud for everyone. It's a digital applaud. I believe there's time for like 2 questions, maybe 2 quick questions. So I know there was those movement on the chat. Are those questions still relevant? I would invite those who asked or anybody who has a question to just unmute. And if there is collisions, then I'll moderate that. But
yeah, I think my question is still relevant. So can the proofs be done in parallel?
Yes, for the type 1, yes, you can have them all done in parallel.
Okay,
yeah,
cool.
so otherwise that would be a big round overhead, you're right.
Yes, thank you.
I see there's another question, is there an ongoing effort to formally verify such protocols? Actually, I'm not sure. I'm not fully informed on the progress in that direction. So I don't think any of the recent stuff that I've described, almost certainly not. But there's a good question about what's going on in general in the secure computation area.
Okay, any last question for Elette? Okay, so again, thank you so much, Elette. This was fantastic, and I think I speak for everybody when I say that we really enjoyed it. I'm going to stop the recording, and we'll be publishing it and sending it to everybody.